So, did you like the lecture or enjoy the lecture? So it's yeah. I also watched the lecture videos last night for the 2 lectures that we have to watch, and then yeah, I didn't. Yeah, honestly, I didn't like the lecture much, and yeah, there were many derivations. Yeah, yes, and then yeah, many of them are not very intuitive, I think, and then. Uh, Although the lecture gives like 4 different perspectives of understanding backpropagation, but yeah, yeah, I couldn't understand properly all of them, and then yeah, I just decided to make sure to understand at least one of them, but not through this lecture, but the lecture that I watched previously, which is from CS231N. Okay, so that is yeah, I think many of you know already, but this lecture of CS231N is like kind of a Bible kind of a lecture for deep learning, although it's yeah, it's focusing on the mainly the vision applications, but still, yeah, it yeah, handles this text or NLP or like RNN and LSTM and so on. So if you haven't, yeah, I strongly encourage you to watch the lecture video on this, especially for the backpropagation. Okay, so it is, yeah, it gives a really comprehensive understanding or explanation about this kind of a kind of circuit design, what circuit design that yeah, Richard Socher is saying or calling, and yeah, so from this say kind of step by step, we can kind of understand many of these complicated neural net functions, and then yeah, so yeah, this website itself doesn't contain. Okay, yeah, so it has these lecture videos, and then like this. Yeah, maybe on yeah, lecture 6 or 7, is it the about the backpropagation or not? So it is not. So which one is about the backpropagation? Yeah, maybe this one. Yeah. So yeah, I strongly encourage you to watch this video, and then you should be able to understand at least the backpropagation. Yeah, yeah, at least with some level. And then yeah, regarding our lecture, so yeah, I'd like to take any questions. So do you guys have any questions? So do you guys all know how we can solve this? Okay, it may be see lecture. So it's about the backpropagation. Okay, so let's just do some simple exercise. X and Y and Z, and then add it and maximize it and multiply it. Okay, it's 1 to 0, so it's 1, 2, and 2, and 0. So here we can first do the backprop forward propagation on this computational graph, right? So let's just fill out the forward propagation and 3, and then the max is 2, and then it will be 6, and then here we set, we usually set the gradient over here as 1, right? And then what is the back, how is backpropagation working on this multiplication? Is it, it is called gradient, what? Although it's from the CS231N, but it's a switcher, okay? Switcher. So this is multiplied with this one, and that will form the gradient over here, right? And then, so this guy and this guy will form the gradient over here. So it will be 2. So we usually write the gradient over here on the below this edge, and then so from this max gate, this gradient, where is it flowing? Where is it flowing? Or let's think about this function of y equals max, maybe x1 and x2, which picks up the maximum value between the x1 and x2. So in this case, let me just test you guys. So given this gradient, what is the gradient over here and here? So over here, what is the gradient? It's a 0. And what about this part? It is 3, right? Okay, great. You guys already studied the CS, maybe, at least the backpropagation quite well. So in this case, let me just derive it simply. So x1 and x2, and if x1 is equal to or greater than x2, and otherwise, like this, right? And so in this case, so we have to do the partial derivatives, dx1, dy over, so this guy, right? dy over dx1, and then in this case, if this is the case, and then if this is satisfied, and then our function, although this one looks complicated, but it's nothing but just the x1, right? So in this case, we are doing the partial derivatives, and thus the gradient will be 1. So we are talking about this case, right? And then the x2 dy, it will be what? 0, because in this case, it can be viewed as ax1 plus maybe bx2, for example. So in this case, what is the partial derivatives with respect to x1? It will be a, and then partial derivative with respect to b, x2 is b, right? And also we also studied about it as a vectorized form, where we have a, b, and x1, x2, and then the gradient vector that just collects the x2 dy will be what? Just this one, a and b, as a column vector, right? So in this case, if we plug this x1 into this form, and then that is corresponding to a being 1 and b being 0, and thus 1, 0 will be our gradient, and we still talk about this case, right? And then the other case, we have an x2, and thus the gradient will be 0, 1. I mean the gradient vector. Okay, then this 3 time will be so this guy will be the maximum one. So it is corresponding to this case when x1 is y and z, right? And thus we have a 3 here, right? Okay, so in this case of a multiplication, student answered that this one works as a gradient switcher, right? So our function z is defined as a times b, and then maybe this one as f, and then it will be b, and the f over db will be a, right? So in this case, gradient will be this guy and this guy for a and b, right? So that's why, yeah, we have this is multiplied to no, this guy will be multiplied to generate this guy, and this guy will be multiplied with this guy to generate this guy, right? So that way gradient will be switched between a and b. Okay, so far so good, right? And then what about the add operator? So in this case, the gradient will be duplicated, right? So it's gradient. What was that? Duplicator? It was not the gradient. Yeah? Distributor, right? Yeah. So that means copying the same gradient into multiple input nodes, and thus this 2 will be placed over here and also over here. But here in this case, y, I mean the gradient of y, what is the gradient? So we have a gradient over here coming from that part, I mean the upper part. Well, yeah, this is a 3. So we also have another gradient coming from the lower part, and thus what is the gradient? What is the gradient corresponding to y? Huh? It's a 5, right? So it's added together, right? It's added. So there is there is something called a multivariate chain rule. Okay, so this is applied, and this one is gradient is added at the branch. So for example, so if we have a node x, and then it has a 2 branches in our computational node, and then the gradient coming from these 2 branches, they will be added together. Okay, and then suppose this one is y1 and y2. Okay, and then maybe we may have more, but eventually our function, I mean our final function, will be the scalar function. I mean the output value will always be scalar. I mean, if you are thinking about the loss function will eventually give a scalar value, although it will add up, or it will take the average of the all the loss or errors over the multiple training data items, but our loss function will be just scalar value, right? And then that means our node, in the final node, it will be like, merged into one single node. So there can be multiple paths over here, but this x, goes through these 2 paths, and then somewhere over here, and then they eventually reach this final scalar value, scalar function f. Okay, so in this case we want to compute this guy. Okay, so in this case it can be represented in this form. Okay, so that means this guy is what? So let me just maybe 1, 2, 3, 4. So what is this green part? What is the corresponding number? It is 2, right? And then this guy is 1, right? And this guy is 4 and 2, right? And so yeah, so this kind of gradient, yeah, when this single node branches through multiple nodes by following this fourth path in our computational graph, the gradient will be all added together. Okay, so that is called this multivariate chain rule. And yeah, at least when I watched the CS231N, or yeah, somewhere in our CS224N lectures, yeah, there were some contents or discussions about this, yeah, this characteristic or this properties, but I couldn't get the intuitive understanding about why it should be true. Yeah, although I mean Justin Johnson or Serena Jung is saying that the gradient should be added in this case, but I couldn't get the intuitive understanding. So I did a little bit of a search. And I found these two videos, at least that gives some intuitive explanations about what it should be true. Okay, so I'm not sure if we have to like. Okay, so let me briefly explain what that is. So in this case, our function, final function f, which is still a scalar value, is represented as x squared times y. Okay, but those x and y are parameterized by the single variable t, right? So in this case, t is our x, and y1 and y2 is corresponding to x and y in this case. Okay, and then they will be participating to form or compute the final function value f. Okay, so it can be viewed as like a branching kind of a structure in our computational graph, starting from single node t, and then it branches out into x and y, and then they are merged together into the final node f. Okay, and then here we start from some t. I mean, this is about kind of a forward path. Okay, forward path. So we have a particular value of t. Maybe t could be maybe 0 or maybe pi or something like that. And then it will be mapped into like a higher dimensional point in our x and y. So again, x is branching out into multiple nodes, and that can be viewed as like mapping a scalar value into a higher dimensional vector, right? Scalar or one-dimensional value into a high-dimensional or multi-dimensional vector. Okay, so that's what this two-dimensional plot is corresponding to. Okay, so this is a single point in one-dimensional space that will be corresponding to or maps into this point that is in our two-dimensional space where the first and second axis is x and y. Okay, this two-dimensional point will be again mapped into a single value, which is our final function value. Okay, in this case, so in this video, it is just showing this multivariate chain rule that is shown over there. Okay, so it is showing just this example is satisfying. I mean that equation or that kind of property or multivariate chain rule holds true for this particular case of like this. Okay, but yeah, so far, yeah, it didn't give a good understanding. But the next video about this guy, multivariate chain rule intuition. Okay, so in this video, I mean, I encourage you to watch these videos after our class. But the gradient, yeah, so the gradient is about when changing a small bit in our input node t. Okay, and then that will cause some small changes correspondingly in our x and y. So we have, yeah, we are dealing with the two-dimensional point, right? So suppose when changing t into like a slightly larger value, and then this two-dimensional point became this point. Okay? So that in that case, this guy, okay, this guy is our corresponding gradient vector in our this x comma y space, right? And then this change will also cause the small changes in our final function vector, okay? In this, okay? But here in this case, as you can see, this part, which is our kind of total change in this two-dimensional kind of vector space. So this single vector change it into this single vector, right? But this kind of change, or the difference between this and this vector, is decomposed into this changes along the horizontal axis and another changes along the vertical axis. So that means that corresponds to the changes or slight differences along the x-axis and the y-axis, right? And then overall, this change will cause in total this amount of changes in our final function f, right? And that function is due to both this guy, the changes along the x direction and the y direction. So although it's not it's still not a perfect kind of a derivation or really like a complete understanding or proof about what this should be true, but it gives at least some understanding about what this multivariate chain rule should be true. Okay, because this overall gradient or change is decomposed into the sum of these two changes. Okay, and then the gradient is basically maybe some kind of linear operator or something like that. So the sum of these two changes, and then due to these changes, the final changes, okay, is actually decomposed into the changes due to this guy plus or added with the changes due to this guy. Okay. So yeah, at least I kind of became a little bit more comfortable. Okay, so I actually taught this class like a CS231 as a flipped class last semester, but I just skipped that part without giving a detailed explanations. But I felt really uneasy since then. But now I feel a little bit more comfortable. But anyways, yeah. So you can watch this maybe when you have time after the class. Okay, so talking about the backprop, let me discuss another one, another really important properties of. So yeah, often we also consider the computational graphs in terms of a vectorized form. Okay, so in all of these cases, even though x, y, z are can be viewed as a single vector, but this computational graph only deals with the scalar value, right? Scalar value. But usually in our neural nets, we often handle or implement our neural net as a vectorized form, right? So in that case, so yeah, I'm just trying to talk about the linear layer, or yeah, this kind of fully connected layer. So for example, in this case, suppose our vector y is two-dimensional case, and then our input node is a three-dimensional vector, and then what is our W matrix here? It is 2x3 matrix, right? And then let's think about the matrix as 1, 2, 3, and 4, 5, 6. And then in this case, we have three input nodes, x1, x2, x3, and then they are fully connected with y1 and y2, right? So we have all connections, right? Okay, so far so good, right? And then here, as I briefly mentioned, and also as the lecture is also saying, showed, the gradient of d. So this dx is really not a correct representation. So it's not really a dx, but it's df over dx, right? So this is still the partial derivative with the same final function, or which is usually our objective function or loss function, right? So in this case, it is usually represented as this guy, right? So this is our formula that we often apply in our deep learning or this kind of thing. Okay, so I'm gonna just show the derivation about it from this by using this simple case. Okay, so in this case, let's think about the gradient with respect to x1. X1, because in this case, so this is x is a vector. So eventually, what should be the dimension of this guy? Gradient with respect to the vector x. It should be three-dimensional vector, column vector, right? So that is just nothing but a vector representation of individual scalar input node, right? So that means the x1, the x2. Okay, this is nothing but the collection of these partial derivatives with these scalar variables. And then let's just focus on this guy. Okay, so so let's just write two equations separately. So this one is y1 and y2, x1, x2, x3. And then what is y1? y1 is 1 times x1 plus 2 times x2 plus 3 times x3. And what about y2? It's 4 times x1, 5 times x2 plus 6 times x3. Okay, and then let's think about this guy, gradient with respect to x1. Okay, so let's just focus on this node, just like this y. Okay, so in this case, it is actually branching out into two nodes, and thus the gradient coming from both nodes should be added together, right? And then it is the same in this case. So focusing on x1, okay, it is connected with x1 and x2, right? And then what is the weight? So what is the weight? So the weight is it's not about the forward propagation value. It's about representing the weight value, right? Okay, so the weight here is 1 here and 4 here, right? And then suppose we have a gradient over here as dy1 and dy2, and altogether this one is corresponding to this vector, right? dy1 over df and also dy2 df. So that is simply represented as dy1 dy2. Okay, although it's a little bit bad handwriting, but you get the idea, right? Okay, and then suppose our gradient was like maybe 7 and 8. So that was our dy1 and dy2, and then so when doing the partial derivatives with respect to x1 for the first equation or the upper node, and then what is our gradient? It is 1, right? Because we have a coefficient value as 1, right? And then what about this guy, y2? It will have a partial derivative with respect to 4, right? And thus it can be represented as 1 times what? 7 and 4 times 8. Is it correct? Because we are branching, we have two branches, and thus this guy is coming from, the gradient coming from the upper node, and the second guy is coming from the lower node, right? So far everything is clear, right? Okay, and then let's just rewrite it into a vector form, like 1 and 4 and 7 and 8, because we are using this column vector form or column vector representation of dy1 and dy2 as this vector, because this one is dy. Okay. right? So we can represent it that way, right? Okay, and then this one is this guy, df over dx1, right? And then what about this guy, partial derivative with respect to x2? So you get the idea now, and it will be 2 times 7, right? Because it's coming from here, and then 5 times 8, right? And that will be the total partial gradient with respect to x2. And then it will be also represented as 2, 5, and 7, 8. And then also this guy is like 3, 6, and 7, 8, right? And then altogether, if we form this vector, okay, this vector, and then we just concatenate these row vectors, yeah, vertically as individual rows, and then we multiply this dy vector just one time, right? And then row times column will generate the partial derivative with respect to x1, and the second row, like this guy, times the same column vector on the right, yeah, will generate this the second yeah, this guy, partial derivative with respect to x2, right? So this matrix, okay, this matrix is actually the transpose of this matrix W, and thus we have W transpose times this dy as our formula. Okay, although we are just using this specific example, yeah, you may have now like full understanding about what that should be. Any questions so far? And yeah, so let me just yeah, briefly discuss about really a minor thing that actually annoyed me for a while, and that is this guy, this 1. Why do we set it as 1 here? Where is it coming from? What's that? Unit derivatives. So, yep, I think it is right. So, more exactly, it's like d over f d what? F, right? So, whatever function we are given, okay? So, yeah, let me just write this function x, y, z, and then x plus y, and max y comma z, and then we are multiplying it, right? And then this one is our f, and then let's just view it or treat it as just a single x, and then that is just literally f. And then if we just take the partial derivative with respect to f or this x itself as an entire function as just a single variable with of course the degree as 1, and then it will be the derivative will be just 1. So that is always the starting point for when we apply the chain rule, right? So that's why we set here this value as 1. Okay. And then let's see. Let me just also discuss about the sigmoid function. So let's just think about this function. One. Okay, so this is our sigmoid function. Okay, so dx, df, yeah, you can derive the derivative of this guy, right? But once you write it in a simple form, what is that simple form? So suppose it, let's call it as y, and then what is this guy? Or maybe y. So you can of course derive it, but I'm just asking you to give a representation with respect to y, not an input variable x. Okay. So what is the formula? Y times what? Yeah, this is the formula, right? Okay, so you can easily derive it, but I just wanted to discuss briefly about the characteristic about it related to why it is actually causing the gradient vanishing. Okay, so gradient vanishing. So in this case, so what is our sigmoid function? Sigmoid function looks like this, right? So we have a 1 here, right? And then this guy is saying that suppose we are given the input value as 0.3, and in this case, what is the gradient, okay, at this point? And then geometrically in this function shape, the gradient is representing what? The slope of this line, right? And then how do we compute the slope of this line exactly? So that is corresponding to this representation. And this guy is what? The function value itself times 1 minus that function value. So if 0.3 was mapped into like 0.85, for example, okay, and then this guy is representing 0.85 times in 1 minus 0.85, which is 0.15. Okay, so it's basically the multiplication between the two like numbers that are less than 1, right? Because the function value itself is ranging from 0 to 1 in the case of sigmoid, right? The sigmoid function value is ranging from 0 to 1, and thus this representation is just the multiplication of the two numbers that are between 0 and 1. Okay, so in this case of a sigmoid, the slope will always be smaller than 1, although it is all positive numbers, because there is no negative number possibly, right? So in this case, those two like a positive number that are less than 1, and then multiplied together, and then it will generate even smaller number, I mean close to 0, right? And thus when like a passing through the sigmoid gate as a backpropagation, the gradient will be always multiplied with the small number less than 1. So that's why the previous gradient on the right becomes smaller and smaller as we go through the sigmoid gate in the backpropagation. Okay, and then here we can also, I mean, it's a very basic analysis, but this is y minus y squared, and then we can represent it as y minus this guy, and then is it correct? Right? So in this case, if we draw the line, if we draw this case, and then 1 over 2, and maybe 1/4, and something like this, right? But we are only using this ranges for this function from 0 to 1, because this y value itself is output of the sigmoid function value. So these are the function shape of our gradient, and then the maximum gradient value will be like 1/4, I mean 1/4, and that maximum value is achieved where? It is over here, right? So it has the maximum slope at the origin or at the 0 input, and then that maximum slope is only like 1/4, right? Which is still really small value, right? So the gradient will be vanishing by just multiplying this as less than 1 kind of values over and over. So suddenly we are talking about some different properties of our neural net and the backpropagation, and then this is a kind of sigmoid disadvantages, right? So it's notorious for this gradient vanishing, and thus what do we use? As an alternative for this sigmoid? So we use either 10H or another one. It's called ReLU, right? And then why is ReLU like alleviating the gradient vanishing problem? So so you guys are quite familiar with this background about this neural net, but ReLU is something like this, right? So also the ReLU is represented as this guy, right? Okay, so in this case, of course, it is represented x as x if x is greater than or equal to 0 and 0, right? So at least in this case, the gradient, what is the gradient in this case? The gradient will be just simply 1, right? So if our activation is positive value or non-negative value, and then the gradient from the previous node, I mean gradient on the right, will be backpropagated as the same value, right? Without kind of a scaled down values, right? So that's the main benefit of this ReLU function. Okay, but this is really like all or nothing kind of a strategy. Okay, so let me explain what I mean by that. Okay, so let's think about this fully connected layer coming from 3 node into 2 node. Okay, and then maybe they are merged into single node. Okay, so it's like really this kind of a 2-layer neural net, right? By the way, it's called a 2-layer neural net, not the 3-layer, because we do not count the input layer, because input layer is always existing, so we do not count it as a 1 layer, right? So it is called a 2-layer neural net. Okay, so in this case, so suppose we concatenated here as our sigmoid function here, sigmoid. Okay, so suppose our gradient was maybe 7 and 8. Okay, so in this case, as we go through this sigmoid gate, the gradient value of 7 and 8 will be much diminished, or it will be much smaller value, right? But what about the ReLU unit? Okay, so in this case, instead of using sigmoid, we will use ReLU in this case. And then suppose the input activation. So let's think about the forward propagation and their activation, or the input to these ReLU units. And then I'm talking about this the activation of this point, which is a kind of a result of the linear combination from these three input nodes, right? So suppose the activation was 3, for example, and then here the activation was -4. Okay, so in this case, given the gradient value of 7, what is the gradient value over here? So this is again ReLU. And yeah, so I have to write 7, not here, but eight. Yeah, it was 7, right? 7 and 8. So because that is our gradient, and then this 3 will be passed through our ReLU as this 3. So this is an activation, and then -4 will go through our ReLU unit, and then the output will be 0, right? And then let's think about the gradient by filling this rectangle here and here. Okay, so in the case of 7, what is the gradient over here? It is 7, because in our ReLU function definition, okay. Yeah, so we have to look at the we have to check the activation of this guy. So this activation is is corresponding to this region. So in that case, the gradient will be 1, and that will be multiplied with the previous gradient, and thus we have 7. But what about this guy? This guy, it will be 0, right? Because it is corresponding to this guy. It is just a constant value, right? Constant value. So taking the derivative for the constant function will be always generating 0. Okay, and then we have a gradient 0, and then chain rule is basically multiplication. It's all composed of the multiplication, and thus this node's gradient will be 0, and then whatever the weight we have here coming from this node, we will have all 0 gradient, right? But what about this node? Yeah, it will have the gradient value 7 as it is, with no scaling down, and then this 7 will be propagated into these input nodes, right? So in this case, I'm not sure how interesting it is, but in this case, we can view this as a kind of all or nothing. So in the case of ReLU, if it wasn't activated, the previous gradient will be flown as same value, and then just backpropagate, right? The same magnitude of a gradient will be preserved from that node. But what about the lower node? That will entirely kill our gradient. Okay. So coming from that node towards the input layers, towards the more lower layers, there will be no gradient flowing back, right? So in that case, if you imagine like a little bit of a light bulb corresponding to all these nodes, and then let's think about light bulb is really shining when they have really big gradient, okay, big gradient, and they are really turned off if they have no gradient. And then if we like imagine about like dynamic kind of animation of this forward and the back propagation, and then when they are back propagated, when using all the nonlinear units as a ReLU, and then only like a sub part in our computational graph or in our entire neural net, only some sub part of the node will be turned on, while the other part will be completely turned off, right? But still, in this case, the lightness of the previous node will be the same. I mean, as long as it is activated by the ReLU or the positive activation, and then the strength of this lightness will not diminish, right? So that's why we avoid this gradient vanishing. But still, there are some subparts of our network that are completely killed. So that way, ReLU is kind of taking like this kind of an all or nothing kind of strategy. I mean, all corresponding to those activated nodes. I mean, that has a positive activation, and then the nothing corresponds to the negative activation. But what about the sigmoid? Okay, let's think about just the sigmoid case. Back to the sigmoid. Okay, sigmoid. And then suppose we had these two gradients as 7 and 8, and then are these gradients becoming completely zero at all in any cases? It will not, right? It will just be multiplied with some non-zero number, right? Non-zero number, but those numbers will all be smaller than, less than 1. So it's like when imagining this light bulb thing, and then all the nodes are kind of turned off, but those light strength of this lightness will be kind of diminishing, right? So in that case, again, the backpropagation gradient to these input nodes will come from only from this node. Okay, only from this node. In the case of red, but in the case of sigmoid, it will the gradient will come from these all the nodes, all the output nodes. Okay. And then so it is also quite an easy question, but back to this ReLU case. These three will be trained, right? These three will be trained because their gradient will still alive, and their magnitude will be the same, right? They are not scaled down. But I need more colors. Let me use this color. Okay, so for these three nodes will not be trained at all in this particular case, right? And then where are these three nodes? When are they trained? Okay, it is when using different data item, right? So different data item will turn on or will positively activate the ReLU node, right? So for a different training item, and then different part of the network will be turned on, and thus the backprop will also train that corresponding sub part of our network. But depending on the training sets, training data item, if the training data item is different, and then different part of the subnetwork will be activated, and thus, such kind of a different subpart of our network will be trained from our data set. But in the case of sigmoid, for each data item, will actually change all the weights in our entire network, right? But in this case, the lower part, lower layer will have a really small gradient, right? So I'm not sure how interesting it is, but at least I thought it could be kind of interesting, kind of a intuitive kind of difference between like a ReLU and the sigmoid-based training of our neural net. Any other questions? Okay, and then I'd like to discuss a little bit more about the word embedding. Okay, so the word embedding. So, do you guys all know how the negative sampling works? Right? Negative sampling works. Right? Okay, it's a little. Let me see. I'm looking for the. Okay, during the figure that I drew for the word to back, but so where is it? Yeah, where is it? Is it in? Oh, yeah, there it is. Okay, so you remember this figure, right? Although it's quite messy, but here, for the negative sampling, we actually change. In our output node, it's a little bit messy, but in the output node, that has the same number of our dictionary. Suppose our dictionary has only 5 words, 1, 2, 3, 4, and then softmax vector. Yeah, suppose our softmax vector may have maybe 0.1, 0.2, 0.3, 0.35, and 0.05. Right. So in this case, yeah, suppose this is our softmax function. I mean softmax output, but our output should have been really like this word. So this word corresponding to maybe mass, and then input was given as maybe study. Okay. So in this case, we are just plugging the one-up vector here, right? And then in this softmax layer, you guys know how the gradient is represented. So I think the homework had the derivation of the softmax gradient, but what is the gradient? The gradient is just this guy minus this vector, right? And then the loss is, yeah, caused or loss is generated in all nodes, right? So that way we do the backpropagation coming from all the output node, and then our neural net is trained, right? But in the case of the sigmoid or the negative sampling, so we actually use the sigmoid individually on each of our output node, right? And then that, suppose that output was like 0.3, 0.7, 0.4, and 0.8, maybe 0.2. So of course, each of these outputs are the sigmoid output, and thus they are ranging from 0 to 1, but they are not summing up to 1, right? And then here, yeah, we can. So the reason why we use this sigmoid as our final output activation was because, yeah, we only care about this found word or this observed word as an output word or context word, which is a mass, and thus we only apply the loss over here in this node corresponding to this mass word, right? And then the backpropagation will be just starting from only this node, not from any other output node, right? And then the negative sampling works in a way that we just randomly sample among the other 4 not selected nodes or unobserved words, right? And those unobserved words, let's suppose we picked up this guy and this guy, and then for these two randomly selected nodes that we, yeah, among the many of the output nodes, right? Suppose the negative sampling parameter was like 2, and then it is corresponding to, yeah, sample or, yeah, obtain the random sample as the 2 random samples out of the unobserved words. So if we had a 5 words, yeah, it is actually like contains or include the observed words as well. So we do the random sample from these entire 5 words in our vocabulary or in our dictionary, and then suppose these 2 were selected, right? And then these are the negative samples that we randomly selected, and then what should be the target output for this node? So these 2 are unobserved words, right? And so the target output should be 0, right? And then the gradient will be, yeah, flowing from these 2 nodes as well. So these are the negative sampling. And then here the question is the distribution or the underlying distribution that we obtain these random samples for our negative samples. So we have, yeah, we also include this observed word as well. So in some cases that also can be sampled as well, okay? But then it really is counterintuitive, because if it was sampled as a negative sample, and then as a positive sample, we are applying the label as 1. But then we are also retrain our model once again by applying the label as 0. So that is really conflicting or contradictory, but yeah, they are, I mean, the word2vec or any other kind of negative sampling kind of algorithm is just doing that anyways, because sampling that particular observed word will be usually really small, because in our vocabulary the number of words are maybe usually like more than like hundreds of not hundreds of thousands, but at least 10,000 or so. And so picking up that particular single observed word will be, I mean, the probability will be really small. But anyways, here we can think about the probability that we obtain our sample from, and then the default probability will be, so over these 5 different words, right? 5 different words. Let's think about the probability distribution, and then we can also think about this uniform distribution, which means that each word will have the exact same probability to be sampled as a negative sample, right? So in that case, the probability will be like the number of vocabulary size, 1 over this, right? Yeah, so far so good, right? But we do not use this probability actually, right? So I was, I'm trying to describe the underlying probability that we actually use for our negative sampling, and that is corresponding to, I cannot find the exact pages, but let's just write it in this manner. So we are using this a little bit weird probability distribution as the underlying distribution that we obtain the sample from, right? So let me just briefly describe how this works. So this is based on like the term frequency, or the total number of occurrences of each word, right? So in the case, in our case, our dictionary was this guy I, and maybe study, and this guy was maybe the, and this mess, and maybe this guy is M. Okay, and then this I study, the mess, M. Okay, so in this case we can think of how many times each of these words appeared in our corpus, right? So in this I, suppose it appeared maybe 20 times, and study, it was like 5 times, and then this guy, the, is quite often found, so it was found like 70 times, and then maybe 3 times, and maybe it was like 45 times. So we can think of this term frequency of each word, right, in our vocabulary, in our corpus, entire corpus, right? Okay, so that is corresponding to this TF. I mean, what I meant was term frequency in our entire vocabulary, or no, not entire vocabulary, but entire corpus. Okay, and then here we actually use the multinomial distribution, or this probability value proportional to these values, but not exactly proportional, but we do like this, exponentiating like this for 3 over 4, things like that. Okay, so here the intuition is, in order to obtain the negative sample, we want to obtain such keywords that quite frequently appeared in our corpus, right? So that means, like, if our observed word was mess, currently our current word was mess, but what should be our negative sample? I mean, in the case of like a dog, okay, so that is like a really frequently found word, right? But this particular time, I mean, in this time particularly, it was not observed, right? But overall, it is quite frequently observed, right? So that means that is likely to be our observed word, but in this particular case, it was not observed, right? And thus, we have to use it as a kind of more, I mean, we have to make that or use that heavily as more heavily as a negative sample or a negative word that was not, in order to explicitly say our model that that particular word was not appeared, didn't appear in this particular example case of like study, comma, math case. Okay, so again, if we do not know about the target word yet, okay, if we do not know what the observed word yet, okay, and then we can kind of guess like what is the most likely word, and that will be corresponding to the, right? But in this particular case, it didn't appear, right? And thus we have to use it explicitly as our negative sample with the more kind of more often. But yeah, so that is our intuition for this negative sample sampling underlying distribution, which is in proportional to these term frequency. But we do not use that term frequency as it is, but we use these, right? So these are kind of a smoothing kind of effect. So suppose yeah, we consider these two numbers, 1 and 2, and then yeah, this is 1 and 2. The height is 1 and 2, and then if it is maybe yeah, to the power of like 3, and then the difference between these two bar height, I mean the height difference between these two bar will be more exaggerated, right? But if it is like 1/2, right, and then it is less than 1, and then that will actually make the difference between different bars, I mean the height difference between different bars, to be more like the same with each other, right? So that way, by applying this 3/4, we are trying to make really like all different distributions into a little bit more like uniform kind of distribution, right? So in that case, I suppose I was maybe appeared only 3 times, but it was appeared maybe 3,000 times, and then this guy will be likely to be sampled with a maybe 1,000 times more, right? With 1,000 times a higher probability. But yeah, we don't want that. We don't want that kind of extreme kind of distribution, right? So we want to like maybe 5 and 10, 1,000, so that the bar difference can be more like the same. I mean, yeah. So this is the negative underlying distribution that we use actually in our negative sample. And how did we find this number? So this is just a hyperparameter. Okay. So this inventor of word to bag or the glove, and then they tried many different values, and then did some evaluation about which value is generating the highest performance value for various tasks, right? So this 3/4 is kind of a magic number that they found as a kind of optimal exponent. Okay. Okay. So yeah, let's take a break for 10 minutes, and then let's start at 3:30. 네.
질문은 아니고 제가 이해한 게 맞는지 한번 확인해보고 싶은데 이제 그 그레디언트 미분하면은 이렇게 표현되잖아요.
네.
얘가
네. 네, 지금 여기 1-y.
네.
네.
이렇게 되면
네.
x 이렇게 되는 거구나. 맞죠?
네.
네. 근데 얘가 이제 뭐 fx라고 치는 x 마이너스 x 얘가 결국에 fx 마이너스 x
네.
이게 그림상으로 나오는
네.
이렇게 결국에는 그래던트를 큰걸 이 그래던 값 자체가 될 수 있으니까
네.
이제 어떤 점을 x로 잡아도
네.
결국에는 여기가 크면 결국에는 마이너스 x로
그렇죠. 네.
어쨌든 어떻게 해도 잘 적는다는 얘기를 해도 되는 거죠.
그렇죠. 네. 그리고 이렇게 두 개 곱을 하되 1이라는 어떤 총 어떤 양을 두 개의 값으로 나누는 거예요. 그다음에 그걸 곱해서 우리는 만드는 게 저 기본적인 저 식이잖아요. 네. 그래서 하나가 크면 곱해지는 다른 하나가 작기 때문에 실제로 곱했을 땐 더 작아지는 거예요.
항상 작아지는 경우가 기억할수록
네. 그렇죠. 그리고 이게 기본적으로는 이게 0에서 이게 이 쉐입에서도 보면 0에서 이게 그 슬롭이 제일 가파르고 점점 완만해지고 또 점점 완만해지니까 이게 또 이 식에서는 나타내지는 것이고 그게 아까 저 2차 함수를 그냥 저기 최대 최소해갖고 그린 그렇게 나타나는 거예요.
모든 게 다 그런 거 아니야? 결국 그 네거티브 샘플링에서 이미 잘 된다니까 지금 답이 된 것 같긴 하지만 그 디스트리뷰션이 다른 디스 예를 들어서 간대생각에서 다이그램을 쓸 수도 있고 더 복잡한 디스트리뷰션을 쓸 수 있는데 어떻게 보면은 성 프리퀀시로 그걸 잡아버리면 그 가중치를 주는 거랑 비슷한 효과가 나잖아요. 그걸 업데이트를 더하게 되니까 여러 번 결국에 많이 하게 돼요.
맞아요. 네.
근데 그렇게 해도 잘 나오니까
네.
더 복잡한 디스트리뷰션 안 쓰는 거예요.
네. 그러니까 그게 그러니까 실제로 텀 프리퀀시가 많이 발견된 애가 실제로 지금 이야기한 것처럼 네거티브 샘플링에서도 더 많이 잡혀서 걔가 누군가 하여튼 저 더 멀어지도록 트레이닝이 되는 거예요. 더.
네.
근데 중요한 건 또 걔가 그렇게 많이 트레이닝된 게 네거티브 샘플링으로서도 많이 트레이닝 되겠지만 걔는 기본적으로 그 자주 나타나기 때문에 그 파지티브한 케이스로도 굉장히 많이 나타날 거예요.
네.
걔는 하여튼 누구랑 또 계속 가까워지도록 이렇게 여러 번에 걸쳐서 이제 트레이닝이 될 건데 또 동시에 걔가 안 나오는 그러니까 좀 드물긴 하나 얘가 대부분 많이 나타나는데 얘가 안 나오는 그 드문 케이스에서는 최대한 얘를 네거티브 샘플로 써서 이제 그때 나오는 어떤 이거를 멀어지도록 하자.
즉 그 디스트리뷰션 써도 성능이 잘 나오니까
네.
이제 이걸 쓰는 이유가 다른 것도 다 실험해봤는데 얘가 제일
그런 것 같아요.
계산도 잘 되고
네.
간단하니까 쓰는
그렇죠. 그러니까 나도 뭐 저게 얼마나 다양한 이제 펑션 클래스에 대해서 저걸 실험을 했는지 모르겠지만, 네 일단은 저런 텀 프리퀀시에 이제 비례하다라고 일단은 모델 클래스를 세워놓고 거기서 지수 승에 해당하는 것만 우리의 하이퍼 파라미터로 이렇게 세팅을 해서 그것만 바꿔봤을 수도 있고, 아니면 뭐 그 펑션 뭐 예를 들면 로그의 프리퀀시 같은 로그의 텀 프리퀀시 써도 이게 대충 스무딩이 되거든요. 그게 4분의 3 승한, 네, 4분의 3 승하는 거랑 뭐 대충 비슷해져요. 왜냐면 아주 큰 값은 이렇게 로그가 이렇게 증가하니까 텀 프리퀀시가 굉장히 커도 이 차이는 그렇게 크지 않거든요. 그러니까 로그도 또 하나의 어떤 이렇게 가능한 초이스가 될 수 있고, 네. 근데 이게 좀 뭐 하다 보니 한도 끝도 없는데 뭐 여러 가지 아마 굉장히 이제 익스텐시브하게 실험을 했을 거예요. 모르겠어요. 뭐. 저게 그냥 제일 그래도 무난하게 여러 태스크에서 잘 동작하더라. 네.
네거티브 샘플링 공부하면서 같이 나오던 게 하이리컬 스포트너스 막 나오더라고요.
아, 네.
혹시 이거에 대해서 좀 알 수 있어요? 정보가 너무 적어서 네거티브 샘플링이
네, 이게
잘 안 쓰이는 방법이에요.
네, 잘 안 쓰여요. 이게.
아,
이게 어렵기는 좀 많이 어려운데
네네.
이게 좀 잘 안 쓰이고요.
네네.
이게 기본적인 포인트는 뭐냐면
네네.
이게 아까 그 소프트맥스를 이제 시그모이드로 바꾸는 거는
네네.
소프트맥스라는 거 자체가 그러니까 상대적인 프로바빌리티 계산해야 되니까 일단은 아웃풋 노드들에 해당하는 그 액티베이션 값을 싹 다 계산을
네네.
해야 돼요.
네네.
그게 이제 어려운 거. 그러니까 그게 계산이 너무 많기 때문에 그런 거고, 시그모이드는 고 선형, 고 노드로 빠지는 그 선형 아웃풋, 리니어 트랜스포메이션 아웃풋을 가지고 시그모이드 변환해주면 나오는 거예요. 그러니까 그거 한 놈만 계산하면 되는 거예요. 오케이. Thank you. Thank you very much. 네. 그래서 이게 총 보캐뷸러리 사이즈가 5개, 뭐 5개가 굉장히 작은 숫자긴 하지만 5개인데 이제 한 노드에 해당하는 아웃풋만 계산하면 되는 게 이제 시그모이드의 장점이고, 그 다음에 네거티브 샘플링은 이제 그거 하나를 제외하고 내가 네거티브 샘플링 파라미터를 네거티브 샘플링 횟수를 2라고 하겠다. 그러면 2개를 내가 더 해갖고 한 데이터 아이템당 내가 파지티브 샘플 한 놈, 그 노드 하나와 네거티브리 샘플된 거 2개 해갖고 총 3개를 내가 트레이닝을 하겠다는 뜻이고요. 지금 하이라키컬 소프트맥스는 기본적으로 소프트맥스라는 이 전체 모드를 다 계산하는 거를 사용을 하는 거예요. 즉 그 말은 이 5개의 모든 노드가 있으면 그 노드들의 그 모든 노드의 아웃풋을 그러니까 싹 다 그 선형 변환을 해갖고 그 5개 노드에 대한 아웃풋 다 뽑아내고 그거를 익스포넨시에이트, 그러니까 e to the power of something 해갖고 그 다음에 그걸 노멀라이즈를 하는 소프트맥스를 거치는 게 오리지널 소프트맥스라면, 하이라키컬 소프트맥스는 이거를 어떻게 하냐면 5개가 아니라 로그의 5개만큼만 그 선형 변환을 해도 되고, 그러니까 샘플의 개념이 아니라요. 이게 좀 기존의 5개 노드로에 나오는 그 어떤 소프트맥스 벡터를, 그러니까 소프트맥스 아웃풋으로서 아까 이야기했던 요런 이제 소프트맥스 아웃풋 벡터 있잖아요. 요 놈을 계산하려면 5개 노드 아웃풋을 싹 다 계산해야 되고요. 근데 이거를 근사적으로 로그의 5개만큼의 선형 변환만 해갖고 저걸 계산할 수가 있다는 게 이제 하이라키컬 소프트맥스거든요.
그게 이거랑 같은 이유로 변화 이렇게 됐나?
그러니까 그게 약간 이게 인투이션은 좀 그런 거예요. 그러니까 그게 아웃풋 노드가 어떤 뭐 스터디가 들어왔어요. 그랬는데 아웃풋 노드 중에서 비슷한 의미를 가지는 아웃풋 노드, 그러니까 비슷한 노드를 가지는 컨텍스트 워드가 있어요. 예를 들면 뭐 매스, 사이언스, 그러니까 매스가 스터디, 그러니까 사이언스가 스터디랑 비슷하다는 게 아니라 매스와 사이언스끼리 비슷해요. 그죠? 그 다음엔 또 예를 들면 이 스터디랑은 전혀 어울리진 않지만 뭐 바스켓볼, 사커, 뭐 빌리어즈 이런 애들은 대충 또 비슷한 벡터라고 쳐봐요. 그러면 얘네들은 다 벡터들은 비슷하나 하나씩 다 다른 표현형을 갖고 있고, 그러면 이 인풋에서 들어온 스터디라는 인풋 그 센터 워드의 벡터와 이 각각의 워드들이 다 이렇게 내적이 돼서 나오는 값을 소프트맥스에 이제 참여를 시켜야 되는데, 이걸 어떻게 하는 거냐? 이 비슷한 단어는, 그러니까 아까 얘기했던 뭐 바스켓볼, 사커, 그다음에 빌리어즈는 얘네들을 한 벡터로 어프락시메이트 시키는 거예요.
그런 식으로.
네. 그러니까 약간 그런 식으로 해갖고 총 5개의 그러니까 총 이 우리가 5개에 대한 그 소프트맥스 벡터는 다 뽑아내니까, 근데 이제 5개 하나하나의 인디비주얼 워드들의 컨텍스트 벡터와 인풋 워드를 다 내적을 시키는 게 아니라 여기서 뭔가 로그 5개만큼만의 어떤 내적을 통해서 이 5개를 싹 다 나타내자, 약간 이런 식이에요. 그게 이제 하이라키 소프트맥스인데 좀 내용은 좀 어려운데 이제 그러니까 결론적으로 얘기하면 이거가 성능이 잘 생각보다 안 나와서 이제 잘 안 써요. 그 여기 릭스 다 깔아왔나요? 릭스 깔아서 노트북 다 가져왔나요? 깔고 있어요? 그 좀 여러 개를 깔아야 되거든요. 믹텍도 맥에서는 이게 레이텍 그게 뭔지 모르겠는데 뭐더라? 맥텍인가? 뭐 그런 거 맥텍인가 그런 거 깔아야 될 텐데.
나 포기해가지고.
네. 그래요?
스크립트를 안 써줄 모르는데.
그래요? 윈도우까지밖에 안 깔아먹고. 이게 항상 개발한 거 세팅하는 게 제일 어려운 일이라. 렐루가 왜 난리니어냐고요? 일단 직선의 방정식이 아니면 이제 리니어가 아니고요. 그 다음에 이제 리니어하다는 게 정의가 뭐냐 측면에서 보면 리니어의 정의가 뭔가요? 리니어죠.
차원이 바뀌지 않는.
차원이 바뀌지 않는 거? 저기 okay, so yeah, the student asked one simple but kind of interesting question that about whether the value is linear or non-linear function. Let's say non-linear function, okay, and then why is it non-linear, or why is it not a linear function? And in other words, what is the requirement so that a function can be a linear function? What is the requirement to be a linear function? Yeah, because maybe I know well because I teach often the linear algebra. But the requirement to be a linear function is as follows. So we are given x and x1 and x2 as two inputs, and then we have a function f, the same function f, and then we go through this function. Okay, and then let's consider maybe ax1 and bx2 and plus. And then let's think about this a single input. Okay, and then we can go through, we can pass through this as our into the same function, and then we can think of our output, right? And then let's call that output as maybe z, maybe y prime, for example, and then it is nothing but f of ax1 plus bx2, right? And then okay, so y2 is so in this case y2 is of course the function output from x1 and x2, right? And then we have these two outputs, right? And then we considered these a linear combination of these input, right? So we first do the linear combination of the input and then pass through our function, and then we consider that output, and then we also obtain these output from these individual input, and then we linearly combine them later, okay, for these. And then if these are the same as this, and if it is always true, and then this function is linear, okay. Okay, and then back to the function of a ReLU. So why is it not a linear? And then simply in order to prove it is non-linear function, we can simply find one. It is just enough to find one single counter example that doesn't satisfy this, right? Because that should always be satisfied for any of x1, x2 in our domain, or all the possible inputs defined for our function, right? So in that case, it's a linear function. But if we can find at least one kind of single counter example, and then our function is not a linear function. Okay, so let me try it. Let me try a few examples. Suppose 2 and -3, and then ReLU output will be like this, right? And then we just simply multiply it by 1 and then add it together, which is just a particular linear combination by using these two ways as ones, right? So this is one linear combination, right? And then the -1 will be our linear combination of these two inputs, and then our ReLU function will give 0, right? And then what is the linear combination of these two? So 1 and 1 and plus will be 2, right? So this is certainly not the same or not equal to these. So that way this ReLU is not a linear function. Okay, so I think I have shown this in some of my previous classes at least a few times, but so probably you guys know this website called a neural net playground. Okay, so in this case, okay, so suppose we are using this sigmoid and then try to classify this. I'm not sure if it's trained or not, but yeah. It's really difficult to actually fit this training data, but okay, now it's finally trained. Okay, so in this case, yeah, so it is like forming this nonlinear decision boundaries, right? This is when we use the sigmoid, right? But if we use ReLU in this case, okay, so can you see the difference? So instead of like a smooth kind of decision boundary, it's actually a kind of piecewise linear kind of decision boundaries, right? So in the case of ReLU, just before applying the ReLU, we had a kind of a linear function. So if we think of like a y equals ax plus b, that is simply just a linear boundary. But in this linear boundary, so suppose this is our y equals ax plus b, and then this is our x input node and y is a kind of output node, and then it can be viewed as this kind of a really simple neural net, right? And then maybe it can be like 2x plus 3, okay? And then what does a ReLU do in this case, or what does a sigmoid do in this case? So sigmoid is like squashing, like sigmoid is looking like this, right? So the input to this sigmoid is ranging from negative infinity to positive infinity, right? And then around here, the mapping is something like y equals x. So they will preserve the same input as the same output around this origin. Okay, but what about these regions? Okay, these regions will be much squashed into a smaller region. So if you think of this region as maybe 1,000, maybe from 10 to maybe 10,000. Okay? And then the difference in terms of a y output will be really, really small. Okay, so again, this part will be just preserved in terms of their magnitude difference. But as the value gets larger, or into the extreme values, and then their difference will be really small. And so, yeah, I cannot really draw in this case, but yeah, where is the region that is preserved or squashed much? So in this case, so this y values will be our input to the sigmoid function, right? And so around these values, right? Because like these values or y values, they will be kind of preserved, right? But as it gets farther and farther from the origin, they will be really squashed into really like a small value, right? So in that case, what will be our like decision boundary in this case? Suppose this was the original decision boundary represented by that exact linear transformation, but suppose we apply the sigma, and then what will be our function shape? Okay, what will be our function shape? So this function value will be much smaller value, right? So this one will be going to this value somewhere, right? And then this value also will be moved somewhere here, right? And so this kind of decision boundary will be like something like this, right? And then of course, this one is um, yeah, right. 이게 아니죠. Okay, so yeah, so this is changing actually the sign. I mean the negative values into the positive values. So for example, for here, negative 100 will be close to zero value, but it will be positive value. So yeah, that actually makes me that actually confused me. But let's think about like a 10H for example. So 10H is something like this, and then suppose we apply this, and then the same kind of argument applies in the same manner. So around the x range is around the 0, and then that will preserve the original values, but as it gets larger and larger, and then it will be kept into like -1 and +1, right? And so it's like you can kind of get the idea about this kind of distortion of this straight line into this curved line, right? And so if we have a additional node, suppose we had the second layer having a multiple nodes, and then this guy will have also its own linear transformation representation. So if this guy was 2x plus 3, and then suppose this guy was maybe y equals negative x plus maybe 5. So we have its own linear kind of shape, right? And then that will be distorted by our 10H in their own manner, okay? And then they will be also merged together in the layer node, right? So we are distorting a straight line in our own manner, and then we are combining those curved line into a more complex shape of line. So that way we have a really like a smooth one, okay? But what about the ReLU? ReLU is like a all or nothing kind of thing. So suppose our line was something like this line, okay? What will be the output from the ReLU? It will be this guy, right? Is it correct? So we have to look at the y value and then consider it as the input to ReLU, right? So the regions for y value being positive will be corresponding to like these regions, right? And thus that will be in that case ReLU will work as just the identity function that doesn't change the function output, right? But what about the negative input values, which is in this case like these values, like this part, that will be like becoming like all 0, right? So ReLU is like cutting our straight line at some point. We can just cut at some point for this really straight line, right? It's like a kind of semi line. 뭐라 그러죠? 한글로 이거 반직선이라고 하는 거 있죠. 반직선. Okay, so we have a really end point there, and then we have really straight line, and then can we cut from there? Okay, can we cut from there? So we can of course cut like in this case we can cut like this. So we can cut from the right, or we can cut from the left. So we can actually manipulate, or we can freely control them by just changing our slope as needed during our training process. And then those like a semi kind of a line, semi kind of a, or one direction. 반직선이 영어로 뭐죠? 모르겠네. 해석을 하려고 했어. Okay. Anyways, that kind of a like a line kind of a segment, okay, that will be combined together, okay, in the next layer. So that's why we have this kind of decision boundary. So you can think of this piecewise linear functions from the ReLU out, because that is actually cut really the straight line. Any other questions? Okay, and then yeah, let me just discuss about the back-to-back. Okay, so back to this word-to-back stuff. So let me just briefly talk about the back-to-back and how it works in terms of its objective function kind of thing. So we have this kind of neural net again, like a butterfly or just a bottleneck architecture, like 5 nodes and maybe 3 internal nodes and also 5 nodes as an output, right? And then you guys know what these two matrices are, like W1 and W2. Okay, so yeah, let's recall or remember that this W1, what is the size? What is the size? It is like a 3 by 5 matrix, right? And then what is our input node? So study comma mass. So yeah, suppose this was study, right? So I'm just rewriting our example. So this was maybe mass, okay? Okay, and then the input node will be, yeah, input vector will be just a one-up vector, having 1 here, right? Oh, no. 1 here corresponding to this study node, right? And then I already mentioned that in this case, the output will be just picking up these column vector, right? And then that column vector will be used as an input to the second layer, which is transformed by W2, and W2 is represented as, oops. So 5 by 3, and this green one is used as an input vector, right? So those green vector is the same, and that is the center word of a study, right? So far, yeah, these are all what we studied already. Yeah, and then the output node will be like these 5 nodes, right? And then that, yeah, this guy, yeah, you guys know that this guy is a inner product similarity, representing the inner product similarity between this input center word or study center word, like and this first context word vector, right? And so on, right? Okay. So in this case, let me just extend it into a back-to-back setting. So in the case of back-to-back, what is a usual setting? Usual setting is, suppose we have just two documents. Okay, so the first document is I study math, and then the second document is I play basketball. Yeah, I know it's a boring sentences, but let's suppose these two are the two documents. Okay, and then from each document, so in the original word2vec, we don't discriminate different documents, right? So given like the entire Wikipedia corpus, for example, the Wikipedia article may be composed of maybe 100 different articles. So one about maybe deep learning, and another about maybe United States, and so on. And then those are different documents, but we just collect them into a single document, and then we only care about the token streams, right? The sequences of our words shown in our entire document corpus, right? Without this differentiating between different documents, right? But in the case of back-to-back, we actually differentiate the documents that this study comma mass pair came from. Okay, so we actually explicitly represent this training pair of a study and mass came from the first document, not the second document. Okay, so this is the first document and the second document, right? And then we usually give this information as a kind of a concatenated additional one-hop vector in addition to our input vector. So what was our input vector? Input vector was 0, 1, 0, 0, right? So the input vector dimension is the same as the number of the vocabulary size, or the number of keywords contained in our vocabulary. But in our input vectors, in our doc2bag, we actually concatenate these one-hot vector for our document ID, right? So if we had a two document, and then two-dimensional one-hot vector is additionally concatenated into that word one-hot vector, okay? Or if we have maybe 100 documents, and then we can just add 100 document and then just represent the document index as a kind of one-hot vector. Okay, so far so good, right? And then now we have the input node, concatenated, with these two nodes, right? And then what is our W1? So now W1 is not a 3x5 matrix, right? So let me see if I can move it properly. Okay, it was moved, but yeah. Okay, so although it's small, but we concatenated the document ID as a one-hot vector, and then our matrix for W1 will be 3x7 now, right? So we have like two additional columns, right? And then suppose our one-hot vector was 1, 0, representing the document index that this particular training data item belongs to, like study mass came from the first document, right? So this is the main doc2bag setting. And then in this case, let's think about the resulting vector over here. So initially in the word2bag, that was picking up this vector, okay, this column vector, and that would be our output. But here in this case, we have two ones, one over here and another one here. So in that case, what is the result? The result is, so we have this vector, right? So those 0, 1, 1, those 0, 1, 0, 0, 0, 1, 0, they will all work as a linear combination coefficient for this column combination of these matrix, right? So for this matrix, we have a 0 coefficient, 1, 0, 0, 0, and 1, 0. So previously, ignoring that, that's how it worked as a picking up this second column, right? In the case of a one-hot vector like 0, 1, 0, 0, 0, right? But in the case of this doc2bag, we have like a one-hot vector over here, and then another one-hot vector representing the document index, and thus the resulting output will be this guy plus this guy. Okay, so basically picking up this vector and this vector corresponding to this one. Okay, we pick up these two, we pick these two up, and then add them together, right? Because they are they are generating a linear combination of these vectors, right? Okay, and so now the addition of these two vectors, okay, the summation of these two vectors will be placed over here, okay, and then the rest of the story will be exactly the same, okay. So so the output word was mass, and then mass was corresponding to here, right? So we want to increase the probability corresponding to here, and what does that mean? So as we already studied, the similarity between this input center word and this guy, the actually observed context word vector, the similarity between these two should be maximized, right? So that way we are maybe making this vector closer to this vector, so that their kind of inner product can become larger, right? So this is the overall kind of a training process, or like overall how this word2bag works. But now this green vector is the summation of these two, right? Summation of these two. So that means not only this vector is becoming close to this observed context word vector, but also our document vector is also getting close to our context word vector or observed context word vector. So this mass vector is placed over here, but yeah, so we also have this, yeah. So basically, this one is representing document one, the vector embedding, the vector representation of the first document, and then this one is another vector representation of the second document, right? All living in the same three-dimensional space, together with all these five words vector, like as a center word vector. Okay, so all the five words and two documents are now living together in the same space. So that is the main problem setting in the doc2vec. And then, yeah, these document, the first document vector is actually getting close to this mess. Okay. So this is basically the doc2vec. So that way we are obtaining the document vector, documents embedding vector as well, in the same word embedding space, in a way that that document vector will be close to those words found in that particular document. Okay. Okay, so like suppose I study math was placed over here, and then maybe, yeah, I is already over here, and then maybe basketball was placed here, and then our document vector is like, so around here will be our document one's vector, and then maybe around here that is close to this guy, and this guy. Corresponding to I play basketball, like so the second document vector is like somewhere over there, close to the words appears in that same document. So this is our doc2vec setting. Any questions so far? Okay, and then this doc2vec setting can be easily extended into like a more number of multi-hot vectors. So in this case, suppose our word pair like a study and math belongs to the first document, which is like a news article published by Naver, for example. Another one was a news article published by maybe Down. And then that document can also have other metadata information, like the first document was written by maybe John, and then the second document was written by Jane, maybe. And then we can also think about this author kind of information that particular kind of training data belongs to, right? In that case, yeah. Okay. So we added another one-hot vector representing the document ID, but we added also, we can add also another kind of a author ID kind of a one-hot vector, okay? And then maybe like a location vector and things like that. So in that case, by simply using just word association, like the pairs of these two words, and then we just slightly concatenate, or we just add additional informations into this word2vec framework, such as like document ID, like gender ID, whether it's a male or female, and then maybe location, and even like a time. If it was written in maybe 7 a.m. in the morning and maybe 9 p.m. in the morning, then we can easily come up with maybe 24-dimensional, like an hourly one-hot vector. So in that case, we can also obtain each hour's embedding vector in this same space, right? So that's how we can kind of utilize this like doc2vec framework. But really, how it works is as follows. Okay, so this is the doc2vec. So any other questions? 뭐 질문 없어요? 나도 미천이 좀 떨어져 가는데. 네.
엑스백이 항상 어떻게 좋다고 하시나요?
그렇지는 않아요. 네. 네. 그러니까 이게 지금 보면 이게 보면 요 지금 보면 요 매스라는 워드에 지금 매스라는 컨텍스트 워드로서의 워드 임베딩 벡터에 요 스터디 벡터의 센터 워드로서의 워드 벡터가 가까워지도록 학습하는 게 월투백이었잖아요. 지금 세팅. 근데 지금 이게 지금 저 스터디의 센터 워드 벡터와 그다음에 요 스터디가 포함된 요 다큐먼트 요 사이언 색깔 뭐 하여튼 요 색깔 벡터가 같이 합산이 돼서 쟤랑 가까워지면 되는 거예요. 그 말은 두 개 다 종합적으로 S에 가까워지도록 하는 거지만 또 동시에 그 말은 약간 우리가 이제 팀플하면 좀 약간 좀 상대방한테 의존할 수 있잖아요. 그래서 스터디라는 게 실제로 온전히 자기 자신이 S에 가까워지도록 되는 게 아니라 얘가 속한 다큐먼트가 S에 충분히 가까우면 자기는 그냥 써. 쟤랑 가까워질 필요가 없고 이런 식으로 어쨌건 이게 좀 나눠먹기를 하는 거니까 기본적으로는 그래서 월투백보다 좋다, 나쁘다. 그렇다고 또 나쁘다라고 이야기하기도 또 약간 그런 것 같고요. 네. 일단은 이거는 기본적으로는 그러니까 많이 쓰이는 어떤 그거는 이제 여러 헤테로지니어스 타입의 이제 그 엔티티들 그러니까 여기서는 기본적으로 이제 월드와 이제 다큐먼트라는 이제 서로 다른 종류의 이제 그 어떤 오브젝트들 혹은 아이템들을 같은 스페이스에 임베딩 했다는 거고 이거를 좀 많이 사람들이 활용을 해요. 그래서 뭐 이런 닥투백 같은 거 그 혹시 그거 저기 월투백 공부할 때 이제 뭐 어떤 좀 머리 긴 남자가 이렇게 좀 프리젠트 하는 거 뭐 베이에리아에서 뭐 프리젠트 하는 무슨 튜토리얼 같은 거를 좀 옛날에 좀 본 기억이 있었는데 이제 이제 뭐 그 스티치 픽스라고 알아요? 스티치 픽스? 뭐 벤처 스타트업 꽤 오래된 거고 뭐 네. 이게 이제 무인 저기 옷 쇼핑몰 이제 웹사이트인데 이게 그러니까 뭐 하도 옛날 일이라 이제 뭐 좀 진부하긴 한데 그냥 거의 가입을 하면 그 웹사이트에 가입을 하면 우리한테 이제 뭐 다달이 그러니까 월에 한 번 아니면 뭐 이제 2주에 한 번씩 그냥 택배를 하나를 보내줘요. 그러면 거기에 이제 옷이 잔뜩 들어있어요. 그러면 그 중에 내가 입고 싶은 옷을 테이크하고 나머지는 그냥 반송을 시키고요. 그 내가 테이크한 옷은 뭐 해당 가격을 내가 후불로 지불하면 돼요. 그러면 다음 달에는 또 핫박스가 또 와요. 그러면 하나도 마음에 드는 게 없다. 그러면 그냥 싹 보내면 되고 전혀 손해 날 게 없는 거예요. 네, 그래서 이게 기본적으로는 추천 시스템. 그러니까 저 사람이 추천 시스템은 기본적으로 두 가지가 있죠. 여기서도 얘기했듯이 뭐 콜라보레이티브 필터링 기반과 이제 컨텐츠 기반이 있어요. 그 컨텐츠 기반은 뭐 약간은 그 어떤 사람, 내가 추천을 뭔가 하고자 하는 그 사람의 그 어떤 피처 혹은 어떤 부가적인 정보를 이용해서 이제 그 사람이 뭐 남자고 혹은 아니 뭐 여자가 되고 뭐 하여튼 남자고 그 다음에 또 20대고 뭐 이렇게 또 뭐 직업은 뭐고 뭐 이렇게 뭐 회사 다닌다 그리고 뭐 와이셔츠 같은 거 많이 산다 뭐 이런 거 있잖아요. 그런 어떤 그 사람의 피처 정보를 이용하는 것이 이제 아마도 이제 컨텐트 베이스드 이제 레커멘더 시스템이고 이제 콜라보레이티브 필터링 베이스드는 그 사람에 대한 정보는 전혀 모른 채 그 사람이 이제 뭔가 흰난방을 뭐 한 3번 샀다는 거죠. 그러면 뭔가 또 다른 뭔가 좀 뭐 회색의 와이셔츠 뭐 그러니까 티셔츠나 후디가 아니라 이제 또 와이셔츠를 좀 뭔가 추천해 주죠. 이런 이제 순수하게 그 구매 이력만을 보고 하는 게 이제 콜라보레이티브 필터링 개념이고 하여튼 그건 그거고 네 그래서 이제 스티치 픽스에서 이제 뭘 했냐면 거기에 이제 뭔가 CTO인가 뭐 CEO인가 하는 뭐 크리스 무디라고 하는 사람이 이제 뭘 했냐면 이제 이런 헤테로지니어스 데이터에 대한 임베딩을 자기네 그 사업에서 이렇게 좀 적용을 해갖고 이제 뭔가를 했어요. 그리고 거기서 이제 임베딩을 한 거는 뭐냐면 옷과 사람을 이제 같이 임베딩을 한 거예요. 옷과 사람. 네, 그럼 똑같아요. 그 사람이 산 이제 옷들이 뚜루룩 있죠. 그러면 그 옷들을 두 개씩 이렇게 페어를 이렇게 짝 짓는 거고 그 사람 아이디를 다 아이디를 하나 주는 거예요. 이렇게 해서 이제 사람 뭐 100명 있고 옷이 뭐 한 500개 옷이 있다. 그럼 총 600개의 토탈 그 아이템들을 한 스페이스에 인베딩을 하고 나면 그 다음에 뭐 그러면 뭐 대략 뭐 거기 그림 뭐 나오는데 옷이 뭐 여기 이렇게 뭐 좀 뭐 여자 블라우스 같은 게 뭐 하얀색 블라우스 여기 뭐 왼쪽 위에 있었나? 맞으면 내 기억이 대단한 건데 뭐 여기 어디 있고 또 저기 어디 뭐 청바지 잔뜩 있고 그리고 거기 유저들이 콕콕 박혀져 있는 거예요. 그러면 기본적으로는 그 유저가 그 아이템들과 이제 시밀러하다라는 그런 이제 성질에 의해서 인베딩이 된 거고 이제 좀 정성적이긴 하지만 퀄러테이티브하긴 하지만 내부적으로는 뭐 여러 가지 빡센 어떤 그 프리딕션 알고리즘 뭐 그 레커멘드 시스템 알고리즘을 돌려서 했겠지만 이 월딩 베딩에서 이제 기본적으로는 이 유저가 이제 요 비슷한 옷들에 가깝게 위치했으니까 요 사람은 이제 요런 옷들을 좋아한다 뭐 이런 것들을 산 거죠. 또 다른 혹시 질문 없나요?
이거는 스튜던트랑 워드와의 관계가 스튜던트를 추천 시스템 예를 들면 스튜던트 유저로 보고 워드를 아이템으로 보고 그런 유저에 대한 정보를 저런 방식으로 만들 수 있는.
그렇죠. 네. 그러니까 이 추천 시스템이 여기서 끝나는 건 아니에요. 그러니까 이 인버딩 벡터 얻었다고 뭐 누구 하나 이 사람이 위치한 곳에 뭐 주변 사실 제일 쉬운 추천 시스템은 그 유저 탁고 이제 인베딩 포인트에 가서 k-nearest neighbor를 따져요. 그래서 가장 가까운 거 순으로 뭐 한 10개 뽑아갖고 박스에 넣어서 보내주면 이제 되는 거고 이제 뭐 이런 식으로 이제 뭐 추천 시스템 자체를 이런 어떤 인베딩으로 이렇게 그냥 다 처리를 해버릴 수도 있지만 사실 우리가 워드 인베딩 가지고 이제 보통 워드 인베딩을 사용을 하는 게 이제 워드 인베딩은 기본적으로 이제 다른 좀 우리가 좀 제대로 뭔가 좀 하고 싶은 뭔가 시리어스한 그런 태스크 서머라이제이션 아니면 QA 뭐 아니면 뭐 이렇게 센티멘트 어널리시스 뭐 이런 여러 좀 우리가 하고자 하는 메인 태스크가 있어서 거기에 이제 인풋 벡터로서 이제 주는 거죠. 근데 그 역할은 기본적으로 뭐냐면 이 태스크 입장에서 볼 때 이 워드들이 하나하나가 다 원합 벡터로 들어왔다라고 하면 그때도 얘기했듯이 그들 간에는 시밀러리티가 다 동일해요. 혹은 유클리디언 디스턴스든 뭐 이너 프로덕으로 따지면 뭐 정확하게 90도니까 다 빵빵빵. 그다음에 이제 유클리디언 디스턴스는 뭐 다 이제 루트 2라는 원합 벡터 두 개가 있어요. 100, 010 이렇게 해보면 유클리디언 디스턴스는 항상 루트 2가 나와요. 이게 디멘전이 100디멘전이라 하더라도 루트 2예요. 뭐 하여튼 그 디멘전으로 무조건 붙박이로 모든 애들이 디스턴스를 싹 다 이렇게 만들어주고 넣는다는 거고 이제 그런 태스크를 할 때 이제 월드 인베딩 벡터를 대신에 넣어준다는 거는 이제 요 벡터랑 요 벡터가 이제 비슷한 애니까 뒤쪽에서 볼 때에도 얘네들은 뭔가 이제 비슷한 어떤 우리가 하고자 하는 어떤 그 뭐 센티멘트 클래시피케이션이다 그러면 애초에 비슷한 의미의 워드는 아마도 요놈 한 놈이 이제 파지티브였다. 그러면 또 다른 요 이제 비슷하게 위치한 그 놈도 파지티브일 거다. 약간 이런 거를 좀 도와주는 거예요. 거꾸로 이제 멀면 또 원대로 또 얘는 좀 다른 패턴이 있을 것 같아라는 그 시밀러리티가 좀 어느 정도 좀 약간 좀 반영이 된 어떤 그런 형태의 인풋을 모델의 어떤 스타팅 포인트로 넣어준다는 그 의미가 있는 거기 때문에 이제 그 추천 시스템에서도 기본적으로는 이제 유저라고 하는 것에 대한 이제 인베딩 벡터를 우리가 일단은 뭐 이런 식으로 만들어 놓는다면 그거를 이제 유저를 나타내는 어떤 독립적인 정보들이 있다면 만약에 그 정보들까지 우리가 활용할 수가 있겠지만 아까 얘기했던 뭐 나이, 뭐 성별 이런 것까지 해갖고 이제 뭔가 그 유저를 나타내는 어떤 부가적인 피처를 이제 집어넣을 수 있겠지만 이제 지금 이 상태에서는 지금 이 상황에서는 일단은 어떤 우리가 추천하고자 하는 대상이 되는 아이템들과 이제 그 유저들 간에 좀 얘가 좀 확률이 좀 추천을 좀 많이 할 만한 것들 인 애들이 일단 이 어떤 우리 스페이스에 좀 이렇게 좀 한데 모여 있으면 그거 가지고 뭔가 제대로 된 추천 시스템에서의 어떤 프리딕션 알고리즘을 트레인을 하면 뭔가 좀 좋은 출발점에서 좀 시작을 하는 게 돼서 뭐 그런 식으로 활용을 하죠. 뭐 하여튼 워드 인베딩 자체는 그냥 뭐 시각화도 해갖고 뭐 서블리니어 아키텍처나 뭐 그런 거 있잖아요. 뭐 이렇게 그런 거 막 이렇게 좀 뭐 재밌네, 흥미롭네, 뭐 이런 거 덧셈 뺄셈 뭐 이런 거 하고 막 그러는데 그거 자체는 사실 뭐 시리어스한 태스크는 아니고 뭐 그거에서 끝나는 게 아니라 워드 인베딩은 다 이제 어떤 기본적인 어떤 하이 퀄러티의 재료를 그냥 제공해주는 그게 딱 어떻게 보면 가장 중요한 의미예요. 또 다른 질문 있나요? Okay, then let's take a look at the quiz. So in this case, if our training data is really small sized, okay, and then in that case we just use a pre-trained word vector, maybe trained from really large corpus like a Wikipedia or something like that, and then we do not change it further, right? So otherwise, our small data, small sized corpus may mess up these word embedding or their similarities, right? Then, yeah, it was a quite easy one. Okay. 뭘 해야 되죠? So since one of the students asked about the hierarchical softmax, okay, hierarchical softmax. Let me just briefly hopefully briefly describe how it works. Let me see. Can anyone tell me the page number, or is it chapter 2 or? Okay, maybe then I'll just describe it from scratch. So hierarchical softmax is basically softmax. So it allows us to compute the softmax vector, which means that in the word-to-vec setting, so we have a input word vector like study, okay, like three-dimensional input center word vector, and then I'm just drawing the same plot 2, 3, 4. Then okay, so the softmax requires to compute this guy times this to generate this, and this guy times this to generate this, right? So in order to compute all these entries, we need like the vocabulary size. I mean the number of inner product computations, the same as the number the vocabulary size, right? So if our vocabulary size is really big, and then this is the big trouble that gives us really a large computation or the computing times, right? So this was the main problem of this softmax based like a word-to-vec, and thus we used a kind of a sigmoid version, and then maybe selectively sample some negative samples, right? So that was the story. But in the case of a hierarchical softmax, so that hierarchical softmax is you can think of a hierarchical softmax is as a kind of way to compute this softmax function approximately by using much fewer number of inner product computation. So in this case, again, this number of inner product computations are needed, right? But in the case of a hierarchical softmax, so roughly we require this many number of inner product computation. So if we have a 400 maybe like 100 different vocabulary size, and then if we use this, and then no, it's log, the base should be what? It should be 2. Okay, so for example, if we have maybe 128 as a vocabulary size, and then we only need 7 number of inner product. And I don't remember exactly how this hierarchical softmax works, because yeah, overall this hierarchical softmax is not used much. So in all the cases, in most of the cases of word embedding applications, people just use a skitgram with a negative sample that we just learned. Okay, but in this case of a hierarchical softmax thing is rarely used. Okay, so in that sense, you can maybe just skip the details about it. But at least this algorithm of this how this hierarchical softmax works is quite interesting, and it's really combining like different knowledge coming from like various literature, like encode signal processing, or like signal compression kind of a theory and things like that. Okay, so in this case, let me just show how it works. So okay, so maybe partially I said wrongly. So yeah, it doesn't compute the entire softmax vector, but it allows us to compute a particular entry for our softmax vector. So this is the value in order to apply our ground truth value as 1 into this node. But previously, when using a sigmoid, this value was just computed independently of all the other values. So all the other value corresponding to other node is not influencing the sigmoid function output of this guy, right? But at least in this case of a hierarchical softmax, it will compute this node value, but this node value is the value when you would have obtained after computing the full softmax. So in other words, the softmax requires all the computation, and then we need to compute the relative probability. So that's why we need all the computations corresponding to each individual node, right? But in the case of a hierarchical softmax, in order to compute this relative probability, still in the context of a softmax vector, which means that the probability will still sum up to 1, right? Unlike the sigmoid, right? In the case of sigmoid, it didn't sum up to 1, right? Okay, and so in order to compute this relative probability corresponding to this node, so you can think of this node as maybe study and math, right? So this is the observed word, right? And then first of what we do is to build up the binary tree. So like this kind of binary tree. Okay. And then the leaf nodes will be our individual keyword contained in our vocabulary. So suppose we have here as math word, and then maybe we have 128 different keywords in our leaf node in our tree, right? And then if we grow this tree in as a binary tree until we obtain that 128 leaf node, right? And then what will be the depth? The depth will be log of 2 128, right? So this is what this number of inner product computation is coming from. Okay. And then you can think of like some kind of gatekeeper. I'm not sure if that is a proper kind of way of describing it, but you can think of each internal node as as having its own vector representation. So in this case, so we are dealing with the three-dimensional word embedding space, right? And so you are assigning each internal node as a three-dimensional vector. Okay, so in this case, you are actually assigning the word embedding vectors on these internal node. Okay, internal node, and then suppose this one is like 1, 2, 3. Okay, suppose that is the word embedding vector corresponding to the root node. Okay, and then at each node we perform the sigmoid operation. Okay, let me show it in detail. Suppose this study vector. Study vector was 1, -1, and 2. So suppose this one is a studies center word vector. Okay, center word vector. And then, as I mentioned, at each node, at each internal node, including the root node, it has its own kind of gatekeeping kind of vector. Okay, so in that case, we compute the inner product between them. So that means that we compute the inner product similarity between them. Okay, and then it will be 1 and -2, -2 plus maybe 6, and then maybe 5. Okay, and then we perform the sigmoid. Okay, so sigmoid will change this value, like, so we have 0 here, and then maybe 5 here, and then let's suppose that sigmoid output, function output from this input of 5 as maybe 80% or 0.8. Okay, so that corresponds to like the sigmoid output of a 0.8 or 80% of the probability. Okay. Okay, so let's suppose this simple node, and then suppose this guy, or maybe this guy, is maybe our mass node. Okay, so in this binary output, yeah, so this mass node is fixed, right? It's like in this particular or fixed order, just following the index in our dictionary. Okay, maybe the first word in our dictionary, second, third, and so on, right? And then given this mass as our target word, and then accordingly, this leaf node will be also fixed. And then what other thing is fixed? Other thing that is fixed is the path coming from the root node into that particular leaf node, right? So in this binary tree, we pick up one particular leaf node, and then let's try to reach, starting from the root node, and then like we follow these branches by following a particular kind of branch among the two, right? At each internal node, and then this particular kind of root is the unique path, right? Unique path, right? There is no other path. So in that case, yeah, so you remember that this probability of 80% as a gatekeeper. Gatekeeper means, yeah, in order for you to go to the right side or right path, you have to pay, or you have to, yeah, pay this amount of a kind of probability reduction. Okay, so suppose you are starting with the 1, which is like the perfect probability of a 100%. Okay, and then as you go through individual internal node, following this fixed path, you are actually discounting or reducing your probability value. Okay, and so 1 times 0.8 will be, yeah, the price or the price reduction coming from 100 to 80%, so that you can go to the right side. Okay, and then this guy also has its own gatekeeping vector. So in that case, suppose that vector was maybe -2, 1, 0. Okay, so this is its own kind of a vector, and then you can compute the inner product with this guy, right? And then yeah, compute the probability value by just computing the sigmoid function. Okay, and suppose that sigmoid function was maybe 0.3, right? And then in that case, 0.3 is the, yeah, so this 0.3 is the probability reduction that you have to pay for by, yeah, so that you can go to right hand side. Okay, so this price the probability reduction, or this kind of scaling factor less than 1 computed by the sigmoid, that is, yeah, you can always think of it as the price reduction or the ratio, so that you can go to the right path. Okay, so this direction is always fixed. And then, but you have to go to left side, right? In that case, what will be the probability? Since this way of probability is 0.3, and then accordingly, this one will be probability of having of 0.7, right? And then starting from 1, you reduce the probability by this amount, and then also you reduce the probability by this amount. So overall, 0.86 is your final probability to reach this leaf node corresponding to our observed world of mass. Okay? So you got the process, right? And then somehow, I don't remember how to prove it, but somehow, once you compute it in this manner, okay? So what is it? What does it exactly mean? What does it exactly mean? So at each node, we have a gatekeeping vector, okay? And then you just keep computing this inner product, and then converting it into sigmoid probability, and then following this path, and then you just multiply these probabilities by following these paths, okay? And then in that case, given this fixed vector, which is coming from the center word of a study, right? And then suppose you are given these fixed vector corresponding to each gatekeeping vector for each node, each internal node, right? Internal node. And in that case, the summation of the all the possible leaf nodes probability will all be summing up to 1. Okay, so this is the main kind of beauty, or like a mathematical kind of a trick that we use. So in that case, even if we didn't compute the probability for all the other unobserved words, right? We only computed the probability to reach out that leaf node of mass, right? But we can still guarantee that if we compute all the other paths and then reaching out different nodes in our leaf node, and then compute the probability, and then if we add them up together, and then they will all be guaranteed to be summing up to 1. Okay, so that way we can at least guarantee that the softmax, the softmax vector, we can guarantee that that probability is actually coming from like a sum to 1 kind of vector, right? So that is kind of a point of this hierarchical softmax, but this is not an exact kind of a method of computing the softmax vector, right? So this is of course really a different way of computing the relative kind of probability, still satisfying sum to 1 vector out of sum to 1 vector, right? But so this is how we kind of approximate this softmax kind of computation in this method. Okay, so again, I mentioned that in order to the softmax probability for this guy, okay, we need this number of inner product computation, but now we need this much smaller number of inner product computations, and that comes from like a fighting or like a matching with each of these gatekeeping vectors at each internal node that we follow in our path.
마지막 밑에 가장 아래 있는 노드에는 단어가 하나씩 들어가요.
네.
그러면 그 위에서 이제 분류를 해주잖아요. 그러면 그 분류해주는 노드에서의 단어가 2개가 있는 거, 2개가 있는 거. 바로 위에.
그렇죠. 그 2개의 단어를 포함하는 이제 노드로서 게이트키핑이라는 게 내가 그러니까 약간 문지기로서 네가 나한테 이제 도착을 했어. 내가 갖고 있는 노드는 뭐 예를 들면 매스와 사이언스가 있는데 네가 이제 사이언스 쪽으로 가려면 나한테 probability 0.7을 지불해라. 혹은 네가 갖고 있는 probability에 70% 깎아먹고 저쪽으로 가라. 이쪽에
그 노드에 예를 들어 노드가 이렇게 내려오면 가는데 그 노드에 있는 단어들끼리 비슷한 단어가
그것도 좋은 지적이고요. 이게 이제 so let me explain how we actually construct this tree. So how do we construct this tree? In advance, right? So in that case, we actually use something called a Hoffman coding or something, which I'm not very familiar with, but that is a kind of capturing kind of co-occurring patterns. Okay, so Hoffman coding is something like this. So yeah, yeah. Beware that I'm not very familiar with the Hoffman coding, but in this Hoffman coding, suppose our kind of a bit sequences that we kind of transmit to the receiver is like 110 and 00110 011 0 1 1 0 1 1 0, for example. Okay, so in this case, suppose we are trying to transmit this sequence of bits to the receiver. Okay, in that case, you you can so I actually did a little bit of tricks in a way that we have like this kind of same patterns are frequently appearing in this bit sequences, right? So in that case, that's when we assign that 3 grams. Okay, that is actually 3 grams, right? So we assign the new this 3 gram and register it into our vocabulary. So initially, our vocabulary was starting from 0 and 1. So if we think about these kind of these as a sequence of our word tokens, and then what is our vocabulary size? It will be just 2, because we have only the 2 words of 0 and 1, right? And then we are expanding our vocabulary or dictionary in a way that if we find the frequent pattern of an n-grams and then we register it, okay, we register, and then like 110 will be added into our vocabulary, and then the dictionary index will be like this one is 1 and this one is 2 and this one is 3. Okay, so in that case, so it's like a binary setting, so it may not be kind of a little bit different, but we just encode this 3 gram as a single word, right, corresponding to the third word. Okay, so in that case, previously it was like a 4 word up to this point, right? But like this guy is 1, is index corresponding to 0, and then in order to transmit these 4 digits or 4 kind of bits, and then if we can just send these 2 numbers, okay, and then if this dictionary is also shared in the receiver side, I mean that's the basic setting for encoding and decoding, like signal compressing kind of thing. So we share this dictionary in advance. So the receiver side, they will know that this 3 is corresponding to 110, and then they are decoding it into original bit sequences like this, right? By just referring to this code book, right? So here the point is that instead of sending 4 different signals, 4 different values, we are now sending only the 2 values, right? So that's how we compress the signal, right? But here, one single number is actually representing a longer sequence of our signals, right? And this is our kind of agreement, or this is commonly shared from the receiver side as well, okay? So this is a kind of encoding or signal compressing or things like that. And using exact kind of same manner, we are encoding this word level kind of binary tree. So let's think about this. Say kind of, I'm not sure what it is exactly called, but is it called a not imbalance tree or something, right? But anyways, let's think about this tree. Maybe this, and so we have like a 4 different words in our vocabulary, okay? And then this node is containing, I mean, how many words are contained in this node? Of course, like 4, right? So, but in this case, it is containing only the 2 nodes, right? And so it you can view this kind of tree construction kind of similar to the previous signal compression case, where if these 4 nodes are frequently co-occurring, just like what was the sequence? Yeah, just like a 110 and things like that. Okay, and in that case, we will encode it into a higher level of internal nodes. Okay, so that way, yeah. So I'm just vaguely explaining it, but kind of similar to the previous case, we can kind of construct this particular trees. I mean the binary trees for the entire dictionaries. Okay. And then in this case, let me just also explain what are actually trained as well. So in the word embedding settings, okay. So I'm just drawing the same figure. So in here, W1 and W2, both of these two parameter sets of W1 and W2 are trained by using our word pairs, right? But this W2 is actually the context word vectors, right? It's a set of context word vectors, right? But if we consider this kind of process, there is no explicit word vectors corresponding to that mass. So the leaf node corresponding to our particular word, that doesn't have any gatekeeping vector. So that doesn't have any vector associated with it. Okay. So here, all these really existing or effective word embedding vectors are all assigned to the internal node, right? Internal node, not to the individual or particular word for their context vector. So we don't assign the context word vector to individual words in our vocabulary in this hierarchical softmax application. Okay. So here we only train like W1, but we also train the word vectors for all these gatekeeping vectors for the entire node instead of the leaf node for our word vectors. So rather than the word vectors as a leaf node in this tree, we actually train or optimize these word vectors corresponding to these internal nodes. Okay. And once we once we have those internal vectors, and then we have no problem of computing the similarity with the center word with the particular context vector or observed word vector, right? And then let's think about the number of gatekeeping vector in this case. So in this tree, the depths will be log v, right? So if we have a 128 the words in our vocabulary, and then we will have a depth of 7, right? And then so depth is 7, so that is easy. But how many number of these gatekeeping vectors do we have in total? 네. v square minus v minus 1요? 네? So we have 2 candidates. Any other suggestions? 올 것 같아요. 네? 또 자, 간단하게 투표 한번 해볼까요? 1번 2번 3번 다시 2번 1번 네, 그래요. 3번이 이제 답이에요. So the third one is the correct answer, right? So you can think of like 128 is 2 to the power of 7, right? And then what will be the internal node? So 2 to the power of 0 is corresponding to the number of node at the highest level, right, in our tree. And then 2 to the power of 1, 2, 3, and what? 2 to the power of 6, right? And then altogether, you know that like x minus 1, x squared, or x0 will be xn minus 1 or something like that. So altogether, this guy times what? 2 minus 1. So this 2 minus 1 is corresponding to x minus 1 because x is 2. And then x to the power of 0, 1, 2, 3, and so on. And then summing up all of them. And then it will be this guy, right? And then what is this guy? This guy is the number of leaf node that we have. And so it will be 128, which is the same as this 2 to the power of 7. But yeah, let's not get confused by this number. This number is just a kind of some kind of an easy number that I just manipulated. So yeah, the leaf node is actually the number of vocabulary size, and then up to the one level higher, and then all summing up, counting all the internal nodes, and then it will be just simply v minus 1, right? So in this case, even though we do not explicitly train the context word vector for individual words in our vocabulary, like a 128 context vector, instead we are training all these internal gatekeeping vectors, which has the number as 127. Okay, one less than the number of our vocabulary. So in terms of the number of total number of parameters that we have to train, okay. So compared to the W2, this tree is actually kind of a comparable number of parameters. Just one word vector, kind of one less word vector, right? Yeah, but still, even though we have really large number of parameters, but for each forward and backward path, yeah, so we only need to compute log v number of computations. Okay, so that is kind of a main point for this hierarchical softmax. Okay, so the time's up. So yeah. So I haven't had a chance to show how we can utilize these leaks, and I believe this is really a useful kind of a useful tool when writing your paper in using a LaTeX. Okay, so yeah, please try to install it in your and then bring your laptop next time. Okay, yeah, okay, thank you, and see you next time.
그 아까 다큐백에서 만약에 워드를 제외하고 다큐먼트 벡터만을 학습하기 원하면은 그렇게 워드 벡터랑 같이 학습하는 거랑 다큐먼트와 워드와의 관계로 학습하는 거랑 어떤 게 더 나은?
그러니까 그 경우는 그러니까 어떻게 보면 이게 페이지가 막 여기 왔다 갔다 해서 좀 그런데 이게 스터디랑 매스가 있으면
네.
스터디 벡터와 또 이 다큐먼트 그 해당 다큐먼트 벡터가 더해져서 얘가 이 매스 벡터랑 가까워져야 되는 거잖아요.
네.
근데 지금 이 세팅을 어떻게 바꿀 수 있냐면 그냥 여기에 다큐먼트 벡터만 넣고
네.
이쪽에 그 다큐먼트에 들어간 워드 벡터만 이렇게 하면
네.
실제로 W1은 이제 다큐먼트에 해당하는 워드 벡터만을 가진 애가 돼요.
네.
다큐먼트 원합 벡터만 쓰면 돼요. 이제 이쪽은 실제로 워드들에 해당하는 그 보캐뷸러리 사이즈만큼의 이제 그 인베딩 벡터를 가진 W2는 그대로일 수 있어요.
네.
그러니까 요 스트래티지가 하나가 있고 요 스트래티지가 하나가 있는데
네.
여기서 아까랑 좀 비슷한 게 이거는 그러니까 두 개가 좀 합심을 해서 얘랑 가까워지면 되는 거예요.
네.
그러면 하나하나는 얘랑 조금은 덜 가까워도 돼요.
네.
근데 여기서는 그 가까워져야 되는 그 책임을 우리의 그 다큐먼트에만 우리가 전가를 시키는 거거든요. 그래서 이게 뭐 좋다 나쁘다의 개념이라기보다는 뭐 이런 특성이 있는 거예요. 그냥.
다큐멘트만을 벡터만을 원하면은
네.
오히려 두 번째가 맞는.
글쎄요. 그게 근데 그게 그러니까 다큐먼트가 진짜 그 해당 그 컨텍스트 워드나 아니면 그 다큐멘트에 나타난 그 워드 벡터랑 가까워져야 된다. 그 책임을 얘한테 오로지 다 전가를 시키는 건 맞는데. 근데 그게 사실 이게 워드 인베딩이라는 게 기본적으로는 이게 좀 애초에 좀 달성할 수가 없는 오브젝티브 펑션이라고 보면 돼요. 왜 그러냐면 지금 이런 한 다큐멘트 내에 있는 여러 개의 워드들이 막 이렇게 흩어져 있어요. 그랬는데 여러 곳에 이렇게 있는 애에서 다큐멘트 하나의 벡터를 얘랑 좀 가깝게 만들었다, 얘랑 가깝게 만들었다, 이렇게 되면 이게 사실 어떻게 해야 될지 갈피를 좀 못 잡을 수가 있어요. 그러니까 이러다 보니까 이제 얘를 이 다큐멘트 하나만 놓고 얘 보고 이제 이 다큐멘트에 나타나는 워드들이랑 다 가깝게 네가 그 어떤 책임을 져야 되는 애다라고 해도 이게 결국은 어찌됐건 대충 가운데쯤에 위치를 하게 되거든요. 이 워드들도 뭐 여기저기서 서로 당기고 막 이러기 때문에 어딘가 적절한 어떤 위치를 잡게 되고, 그렇게 적절하게 잡혀진 위치에서 이렇게 흩어진 어떤 워드들의 벡터들의 다큐멘트 벡터도 어딘가 중간에 들어가는 거예요. 그러니까 하나에만 책임을 전가한다고 해서 얘가 이 여러 개 흩어져 있는, 그래서 어차피 이거를 만족을 하기가 지금 어려운 상황에서의 요거를 좀 더 잘 만족을 한다. 그러니까 이 워드랑 같이 넣어줬을 때보다 좀 더 잘 만족을 한다라고 기대를 하기가 좀 어려울 수 있어요. 그러다 보면 이게 사실 좀 해봐야 되는데, 해봐야지 되는. 근데 아까도 얘기했듯이 뭐 이거든 이제 적당히 다큐멘트에 대한 인베딩 벡터를 뽑았으면 그냥 그거를 그냥 우리는 그냥 인풋에다가 넣어갖고 그냥 쓰거든요. 어떤 태스크. 그러다 보면 뭐 사실 이게 뒤쪽에서, 그러니까 여기가 조금 약간 부족하게 아쉽게 학습이 됐다 하더라도 이 뒤쪽에서 그에 따라서 이제 그 학습 웨이트들이 다 조절이 되기 때문에 사실 사람들이 뭐 요게 더 진짜 요게 더 훨씬 좋은 거다, 요게 더 나쁜 거다, 이거를 사실 사람들이 많이 이렇게 따지진 않는 거예요.
감사합니다.
질문이 있어가지고
네.
그 hierarchical softmax에서 인퍼런스를 할 수가 있나요? 예를 들어 내가 어떤 특정 단어를 뽑아야겠다라는 걸 아는 게 아니고 그래서 맥스 프로바빌리티를 뭐 따라간다든지 빔 서치를 한다든지 하는 식으로 히든 벡터가 있는 상황에서 내가 이피시언트하게 인퍼런스를 할 수가 있는지.
그것도 굉장히 좋은 질문이네요. 되나 그게?
근데 그게 맥스를 따라가면 안 될 것 같거든요.
그렇죠. 그리디하죠.
네. 그래서
안 될 것 같아요. 네.
지금까지 그 네거티브 샘플링이랑 이런 것도 다 아웃풋 단에서 타겟이 있는 상황에서만 그 타겟에 대한
딱 그게 정해진 리프 노드가 정해졌을 때만 그게 좀 유효한데,
제너러티브하게 간다고 할 때
이 중에 뭐가 제일 셀 거냐,
그거 하나를 찾는 데는 결국 소프트맥스를 쓰는 수밖에 없는데.
그러게요. 나도 생각을 못 해봤네. 그러니까 여기서 사실 이게 아마 내가 확실하진 않지만 이 하이라키컬 소프트맥스 기반으로 워드 인베딩을 학습을 하면 저 인터널 그 아까 뭐 게이트 키퍼라고 내가 표현한 그 벡터들은 실제로는 버려요. 그러니까 틀릴 수 있는데 그건 그냥 버릴 거라고 생각을 하고, 그 앞에서 배운 그 W1만 이제 우리가 갖다가 인베딩 벡터로 사용을 하거든요. 그러니까 그 말은 실제 이 프리딕션 태스크로서 이 뒤쪽은 사실 이제 지금 이야기했던 테스트 단 혹은 인퍼런스 단에서 쓰이지 않는다는 의미인 것 같아요. 네. 실제로 쓰는 거를 잘 보지는 못한 것 같아요. 굉장히 좋은 지적인 것 같아요.
다른 스킬 같은 거 그러면 보신 건 없으신 거죠?
다른 경우 저거를 쓴?
그러니까 저걸 썼다기보다는 아웃풋 단에서의 그런 단어 셀렉션? 네. 거기서는 결국 전체 단어에 대해서 프로바빌리티를 다 구하는 수밖에 없는 건지.
그렇죠. 그 이제 소프트맥스를 가지고, 그러니까 이거 하이라키컬 소프트맥스를 가지고 모든 리프 노드들의 프로바빌리티를 구하는 거는 불필요할 거고. 근데 만약에 우리가 학습을 그렇게 해놨다면 모든 프로바빌리티를 구하려면 그렇게 할 수밖에 없잖아요.
그렇죠.
그래서 그 고지고대로 뭔가 테스트 단에서 그냥 그렇게 소프트맥스 대신에 테스트까지 사용할 그런 어떤 의도로 그걸 쓴 거는 뭐 최소한 나는 좀 못 보긴 했는데, 그러니까 근데 가물에 콩 나듯이 저기 하이라키컬 소프트맥스를 좀 활용을 한 그 딥러닝 쪽의 페이퍼들이 조금 나와요. 그러니까 걔네들이 어떻게 저걸 활용했는지는 조금 뭐 다 뭐 용도에 따라서 좀 다를 수도 있고, 뭐 나도 자세히 안 읽어봐서 모르지만 일단은 근데 저게 또 사용이 될 수 있는 어떤 한 가지 가능한 어떤 내가 생각하는 방식은 그 그리디하긴 하나 큰 값에 해당하는 패스를 찾아가서 걔를 어떻게 보면 가장 그래도 여기서 하이스트 프로바빌리티 가지는 애다 라고 하는 게 틀릴 수도 있지만, 그리디한 어프로치라 이게 틀릴 수도 있지만, 그래도 뭐 그렇게 하면 최소한 뭐 우리가 이제 디코딩 할 때 이제 보캐뷸러리 사이즈만큼 다 이렇게 해갖고 소프트맥스 해갖고 하나 뽑는 것보다는 아까 계산 그거 했던 로그 n만큼으로 이제 로그 v v만큼에서 로그 n v만큼으로 이제 계산이 주니까 뭐 그렇게 활용을 할 수도 있지 않을까 싶은데요. 그리디하긴 하나.
빔 서치 같은 것도 활용할 수 있겠죠.
빔 서치 그러니까 탑 랭크드 원을 뽑는 거는 가능한데 이게 세컨 랭크드를 뽑는 게 가능한가요? 맨 마지막에서 2개 뽑으면 되나? 리프노드에서 2개로. 세컨 랭크드, 그러니까 맥스 값은 그냥 큰 값 그리디하게 쫓아가면 되는 건데
네.
두 번째로 클 법한 값을 뽑을 수가 있을까요? 그것도 또 흥미로운 문제인 것 같은데요. 네. 아니 뭐 관심 있으면 더 찾아보세요. 이게 사실 이게 좀 뭐 나름대로 내용이 뭐 저랑 허프만 코딩이니 막 이렇게 실제로 나도 저거 논문에 이제 그 워즈백에 나온 그 식을 보면 아 당최 뭐 하는 건지 전혀 모르겠더라고요. 그러니까 그만큼 이게 좀 뭐 기술적으로는 좀 이렇게 팬시한 그런 게 있어요. 진입장벽이 있어요. 그래서 저걸 이용을 해서 뭔가를 했다라 그러면 실제로 이렇게 자기 이제 연구나 논문에서는 뭔가 좀 사람들이 좀 좋게 봐줄 가능성이 좀 있죠. 네,
감사합니다.
네, 수고했어요.
네.